Dear students, welcome to Digital Learning DCE. Myself Srimati Anupama Godchapnavar, Assistant Professor working in Department of Mathematics, GFGC and PG Center, Gadag. I welcome to all the session 11 and 12 of BSc First Sem Paper 2 Linear Algebra. Set theory and matrices. In that we will discuss the properties of countable and uncountable sets. In the previous session, we have learnt the definition of countable and uncountable sets. Property 1. Definition of property 1 is A is a d-numerable and f is function a tends to b is injective 1 1, then f of a is d-numerable. Proof of this, since a is d-numerable, a is equivalent to capital N. Since f is a function a tends to b is injective and f is a function a tends to f of a is 1 1 and on to a is equivalent to f of a. But a is equivalent to capital N, that implies capital N is equivalent to a since equivalent is symmetric. We have n is equivalent to capital A and a is equivalent to f of a. That implies capital N is equivalent to f of a since equivalent is transitive. That implies f of a is d-numerable. Property 2. Statement of property 2 is a subset of d-numerable is either finite or d-numerable. Proof of this, let A equal to set of a1, a2, so on an be a d-numerable set and b as subset of A. If B is empty, then B is finite. If B is non-empty, let A1 be the first element in A such that A1 belongs to B. Let an2 be the next element of A such that an2 belongs to B, etc. Then B equal to set of a1, an2 and so on. If the set of integers n1, n2 and so on is bounded, then B is finite. Else B is d-numerable since there exists mapping f is a function capital N tends to capital B which is 1 1 and on to. Hence B is either finite or d-numerable. Property 3. Statement of property 3 is n into n is d-numerable. Proof of this, define the function f n into n tends to capital N by f of m comma n is equal to 2 to the power m into 3 to the power n. F is injective. Let f of m comma n equal to f of p comma q. That implies 2 to the power m into 3 to the power n is equal to 2 to the power p into 3 to the power q. That implies m equal to p and n equal to q. That implies m comma n equal to p comma q. Therefore, f is 1 1 function. F is on to every m comma n belongs to n into n. There exists if the function f n into n tends to capital N defined by f of m comma n equal to 2 to the power m into 3 to the power n. Therefore, f is on to. Therefore, n into n is equivalent to f of n into n. But f of n into n is a subset of n is d-numerable. Therefore, n into n is d-numerable. Property 4. The statement of property 4 is the set of all rationals is countable. Proof of this, let q equal to q plus union of null set union of q minus. Define the function f q plus tends to n into n by f of p by q is equal to p comma q. F is 1 1. Let f of p by q equal to f of r by s. That implies p comma q is equal to r comma s. That implies p equal to r, q equal to s. That implies p by q equal to r by s. Therefore, f is 1 1. F is on to every p by q belongs to q plus there exists the function f q plus tends to n into n such that f of p by q equal to p comma q. Therefore, f is on to. Therefore, f is 1 1 and on to. Therefore, q plus is equivalent to f of q plus. But f of q plus is a subset or equal to n into n and n into n is d-numerable. Therefore, f of q plus is denumerable, hence q is denumerable and hence countable. Therefore, q equal to q plus union of null set union of q minus is countable. Then we say that the set of all rationals is countable. Then property 5. The interval, closed interval 0, 1 is non-denumerable. Proof of this, let I equal to closed interval 0, 1. We know that every real number between 0 and 1 can be written in the decimal form. 0.a1 to the power I, a2 to the power I, a3 to the power I and so on, where ai is lies between 0 to a. Let I is the countable, then there exists a bijection function f tends to n tends to the closed interval 0, 1. There exists f of I equal to xi. Every I belongs to capital N. Let xi equal to 0.a1 to the power I, a2 to the power I, a3 to the power I and so on. It is possible to construct a real number x belongs to the closed interval 0, 1 such that x is not equal to xi as follows: x equal to 0.b1, b2, b3, b3, b1, b2, b3 and so on, where bi equal to set of bi equal to when 0 if ai to the power I equal to 1, when bi equal to 1 if ai to the power I is not equal to 1. For example, xi equal to 0.01357, x1 equal to 0.11357, x2 is equal to 0.00357, x3 equal to 0.01157. This means that x1 differs from xi in the first decimal place, x2 in the second decimal place and so on. Hence, x is not equal to xi every I, that is f of I is not equal to x. This contradicts in the fact that f is onto. Hence, the closed interval 0, 1 is uncountable and hence non-denumerable. Okay, then last property of this session, property 6. The statement of property 6 is every infinite set as a countable set. Every infinite set as a countable subset. Proof of this, let A be an infinite set. Let A1 belongs to capital A. Since A is infinite, A is not equal to set of A1. That implies there exists A2 is not equal to A1. There exists A2 belongs to capital A. Since A is infinite, A is not equal to set A1, A2. Continuing like this, we can have a subset B equal to A1, A2, A3 and so on of a set A. If B is finite, then B is countable. If B is infinite, define function f n tends to B by f of k is equal to A of k. Every k belongs to n. Every k belongs to n. Then f is 1, 1 and on to. Therefore, b is equivalent to capital N. That implies b is denumerable. Therefore, we have b is either finite or denumerable. That implies b is countable subset of A. Okay. Use the reference of these two books. Then thank you one and all. Thank you.